close your eyes for a moment and imagine the Earth as it was roughly 13,000 years ago. Before we go any further, if you want a brand new Earth topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. The world you are picturing is not the one we know. It is older, stranger, and in many ways far more alive with mystery than anything we have mapped or measured since. The ice sheets are still enormous. Great walls of glacial ice, some of them more than a mile thick, cover much of what is now Canada and northern Europe. They press down on the land with a weight so vast that the ground beneath them bows like a slow, heavy breath held for thousands of years. The sky above those ice sheets is pale and cold. The air is sharp, and yet something remarkable is happening. The world is warming. For tens of thousands of years, the planet had been locked in the grip of the last great ice age. But slowly, gently, the warmth was returning. Glaciers were pulling back. Coastlines were changing shape as meltwater poured into the seas. Forests were creeping northward, following the retreating cold. Animals were moving into new lands. And somewhere in all of that shifting, breathing world, small groups of humans were walking across open ground that had never felt a human footstep before. This was a world at the edge of transformation. The cold was losing its hold. The ice was giving way. And if you could stand on a hillside somewhere in what we now call the Middle East, or along the wide, shallow coast of what would one day become the North Sea, you might have felt it. A softening in the air, a loosening, the slow, quiet sense that something old was ending and something new was about to begin. We do not know exactly what those people understood about their world. We can only guess at the stories they told, the patterns they noticed in the seasons, the way they read the land and the sky. But we do know they were there. Their tools have been found. Their fires have left marks in the soil. They were watching the world change around them, and they were adapting. Then something happened. Roughly 12,800 years ago, the warming stopped. Not slowly, not gradually. It stopped with a speed that is, even now, difficult to fully understand. Within what some researchers believe may have been as little as a few decades. A blink of time in the long story of the Earth. Temperatures, in parts of the northern hemisphere dropped sharply. Some estimates suggest the drop was dramatic enough to return large regions to near glacial conditions. The ice, which had been retreating, seemed to pause and push back. This cold period is called the Younger Dryas. It takes its name from a small, hardy flower, the Dryas octopetala, a white-petaled plant that grows in cold, rocky soil and whose pollen appears suddenly in the fossil record of this time, spreading across landscapes that had just begun to warm. When geologists and climate scientists find that pollen in ancient lake sediments, they know they are looking at the cold's return. The Younger Dryas lasted for roughly 1,200 years. And then, with the same unsettling speed with which it began, it ended. The warmth came back. The ice retreated again. The world moved forward into the climate we broadly recognize today. But the questions it left behind have never fully been answered. What caused it to begin so suddenly? What caused it to end? And what happened to the people, the animals, and perhaps even the early cultures that were living through it? Some researchers believe the answers are straightforward, rooted in the slow mechanics of ocean currents and melting ice. Others wonder if something far more dramatic was involved, something that fell from the sky or flooded from the land, or both at once. The evidence is real. The cold snap happened. The ice cores confirm it. The pollen confirms it. The bones of vanished animals confirm it. But the cause, the full shape of what unfolded, and what it may have erased from the human story, those questions remain genuinely open. Tonight, we are going to sit with those questions. We are going to move slowly through what the earth remembers from that strange, cold interruption in the warming of the world. And we are going to wonder together about what we still do not know. There is no rush. The mystery has waited 12,000 years. It can wait a little longer while you rest. Somewhere in the middle of Greenland, under more than 2 miles of ice, there are layers so thin you could miss them with a blink. Each layer is a year. Each year is a record. Scientists have drilled down into that ice and pulled up cylinders of frozen time, going back hundreds of thousands of years. What they found inside those cylinders changed how we understand the world. These are called ice cores. Think of them the way you might think of rings inside a very old tree. Every year, a new ring forms. Every year, a new layer of snow falls on Greenland, compresses, and slowly becomes ice. Trapped inside that ice are tiny air bubbles. Those bubbles hold samples of the actual atmosphere from the year the snow fell. The dust in the ice tells scientists how much wind was blowing. The chemistry of the water tells them how warm or cold the air was. It is, in a quiet way, one of the most remarkable things humans have ever figured out how to read. And deep in those cores, at a depth that corresponds to roughly 12,800 years ago, something strange appears. The ice changes. Quite suddenly. Before that layer, the chemistry of the ice tells a story of warming. The great glaciers of the last ice age had been melting for thousands of years. The planet was slowly, steadily becoming more like the world we know today. Forests were spreading. Sea levels were rising. The ice was retreating northward. Then, at that particular layer, the record shifts. The temperature signal drops sharply. Dust increases. The air bubbles show a different mix of gases. Something interrupted the warming. Scientists call this interruption the Younger Dryas. The name comes from a small white flower, the Dryas octopetala, that grows in cold Arctic conditions. Pollen from this flower began appearing in European lake sediments from that same period, far south of where it normally grows. That pollen told early researchers that cold, tundra-like conditions had returned to places that had been warming. The flower became a kind of symbol for the cold snap itself. The Younger Dryas lasted roughly 1,200 years. To put that in perspective, 1,200 years ago, many of the great medieval cathedrals of Europe had not yet been built. The world 1,200 years ago looks almost unrecognizable compared to today. That is how long this cold period held on. Not a brief dip, a long, sustained return to near glacial conditions across much of the northern hemisphere. The ice cores from Greenland show the beginning of the Younger Dryas as something that happened very fast. Some researchers read the data as suggesting the temperature shift took place within decades. A few interpretations push that estimate even shorter, perhaps within a human lifetime. The exact speed is still debated. Ice core data is extraordinarily detailed, but reading it precisely at that depth involves some uncertainty. Different drilling sites give slightly different numbers. Still, the consensus is that the change was rapid by any geological standard. What the ice cores cannot tell us on their own is why it happened. That is where the mystery begins to open up. The cores record the event with great clarity. They show the cold arriving, holding, and then ending. The ending, around 11,700 years ago, appears just as abrupt as the beginning. Some layers in the ice suggest the warming at the close of the Younger Dryas happened in as little as a few decades. Again, the exact timing is contested, and different research teams read the evidence with slightly different conclusions. But the cores themselves are not theories. They are records. They are the closest thing we have to a direct measurement of what the atmosphere was doing during one of the most dramatic climate shifts in human prehistory. They do not speculate. They simply hold the memory of the air. What researchers do with that memory, how they interpret it, what caused the shift, what ended it, and what it meant for the living world at the time. Those are the questions that remain open. The ice is patient. It has been holding these answers, or at least these clues, for more than 12,000 years. It does not rush. It does not explain itself. It simply preserves. And so tonight, as you settle in, think of those long cylinders of ancient ice, resting in cold storage in laboratories in Copenhagen and elsewhere. Think of the air inside them, air that living creatures once breathed, air that blew across a world we can barely imagine. That air has been waiting a very long time for someone to ask the right questions. We are still working out what those questions are. Imagine the world about 12,800 years ago. The great ice sheets that had covered the northern lands for tens of thousands of years were finally pulling back. Glaciers were retreating. Rivers were running free again. The air was warming slowly but surely, and the animals and plants that had huddled at the edges of the ice were beginning to spread back across the land. it must have felt, if anything alive could feel such things across such long stretches of time, like a kind of opening. A slow exhale after a very long cold. And then something stopped it. Within what geologists now believe was a remarkably short window of time, the warming reversed. Temperatures in parts of the northern hemisphere dropped sharply. Some estimates, drawn from the chemical signatures locked inside Greenland ice cores, suggest the shift happened over decades. A few researchers have proposed it may have been even faster than that, perhaps within a single human lifetime, though that remains a subject of careful debate. What the evidence does seem to agree on is this: the change was not gradual in the way we usually imagine ancient climate change to be. It was abrupt. The cold that returned was not mild. Average temperatures in the North Atlantic region fell by somewhere between 10 and 15 degrees Celsius, which is a staggering drop by any measure. Glaciers that had been retreating began to advance again. Sea ice spread back across waters that had recently been open. The tundra, that wide, flat, frozen plain where almost nothing grows, pushed southward once more. The world that had been warming for thousands of years was, in a geological blink, cold again. This period is what scientists now call the Younger Dryas. The name comes from a small flower, the Dryas octopetala, a white-petaled plant that grows in cold, rocky places. When researchers found its pollen preserved in ancient sediment layers across Europe, they knew the climate had returned to something close to full glacial conditions. The flower had come back because the cold had come back. It left its quiet signature in the mud, and thousands of years later, we found it. But the deeper question, the one that still does not have a clean answer, is what caused the freeze to begin in the first place. The most widely discussed explanation involves the ocean. Specifically, it involves a vast system of ocean currents that moves warm water from the tropics northward and cold water southward. A kind of enormous slow pump that helps regulate temperature across the whole planet. Some researchers call this the Atlantic meridional overturning circulation, though most people simply picture it as a giant conveyor belt of water. The theory holds that this circulation slowed dramatically, or possibly even stopped for a time when an enormous pulse of cold, fresh water flooded into the North Atlantic. Where did that fresh water come from? This is where the story gets complicated. One leading idea points to Lake Agassiz, a vast glacial lake that once covered a huge portion of what is now central North America. It was larger than all of the modern Great Lakes combined. As the ice sheets melted, this lake swelled with cold meltwater. The theory suggests that at some point, perhaps when an ice dam gave way, an enormous volume of that cold, fresh water drained catastrophically into the ocean. Fresh water is less dense than salt water. A sudden flood of it into the North Atlantic could have disrupted the delicate balance that keeps the ocean's circulation running. The pump in this picture simply faltered, but not everyone is convinced. This fully explains the speed or the severity of what happened. Some researchers point out that the timing of the Lake Agassiz drainage and the onset of the Younger Dryas cooling is still difficult to pin down precisely. The dates are close, but close is not the same as certain. Others wonder whether a single flood, however large, could really have been enough on its own. There is another idea, more contested and more dramatic, that we will return to in a later part of this story. It involves the possibility that something struck the earth from above, something that may have added its own sudden shock to an already unstable climate. That hypothesis is still being argued over, still being tested, still sitting in the space between intriguing and unproven. For now, what matters is the simple, strange fact of the thing itself. A warming world went cold again. Quickly, the reasons are still being worked out. And in that uncertainty, there is something quietly remarkable. The planet changed faster than we once thought possible, and we are still trying to understand exactly how. Close your eyes for a moment and picture the world as it was 12,800 years ago. Not the world you know, a different one. A world that was, in many ways, still being built. The continents sat in roughly the same places they do today. The mountains stood, the rivers ran, but almost everything else was different. The air was colder, the ice was thicker, and the living things that moved across the land were unlike anything walking the earth right now. What the Younger Dryas did to this world was not slow. That is the part that still puzzles researchers. It did not creep in over thousands of years the way most climate shifts do. It arrived fast. And when it arrived, it remade almost everything it touched. Start with the ice. Before the Younger Dryas, the great ice sheets of the last glacial period had been melting for thousands of years. Glaciers are not just frozen water. They are weight. They press down on the land beneath them with enormous force. When they melt, the land slowly rises, the way a mattress rises when you lift a heavy object off it. This process is called isostatic rebound, which simply means the ground bouncing back after being pressed down for a very long time. That rebound was already underway when the cold returned. And then the cold stopped it. The ice thickened again. The land sank again. The coastlines shifted. Those coastlines are one of the most striking things about this period. Sea levels during the Younger Dryas were much lower than they are today. In some places, land that is now underwater was then dry ground. Wide plains stretched across what is now shallow ocean. Animals walked there. Plants grew there. And if people lived there, which many researchers believe they did, then those places are now buried underwater. Whatever those people built, whatever they left behind, it is sitting on the ocean floor. Most of it has never been found. The air itself was different too. The atmosphere during the Younger Dryas held less carbon dioxide than it does today. Carbon dioxide is a gas that traps heat, and when there is less of it, the world cools. Some researchers think the drop in carbon dioxide helped lock in the cold. Others think the cold came first and caused the drop. The direction of that relationship is still being studied. It is one of those questions where cause and effect are genuinely hard to untangle. The soil tells its own story. In many parts of the northern world, the ground during the Younger Dryas was what geologists call periglacial, meaning it sat just at the edge of the ice, cold enough to freeze and thaw in cycles. That freeze-thaw process breaks rock apart very slowly, grinding it into fine particles. It reshapes valleys. It pushes stones to the surface. It creates a kind of land that looks almost sculpted, hand touched it. Layers of this ancient soil still exist today, buried under newer ground. When researchers dig down and find them, they are reading a record of a world that is gone. The rivers were different too. Meltwater from the retreating glaciers had carved enormous channels across the land. Some of these channels were so wide and so deep that modern rivers look small inside them. The Columbia River in North America runs through valleys far larger than itself. Those valleys were carved by floods that happened before the Younger Dryas, during earlier melt events. But the Younger Dryas interrupted the melting and then ended it all at once. When the warming finally returned, the water moved again, and it moved with tremendous force. One of the open questions about this period is how quickly all of these changes happened together. The ice, the air, the soil, the rivers, the coastlines. Did they shift in sequence, one triggering the next? Or did something happen that set them all moving at once? The ice core records suggest the temperature change at the end of the Younger Dryas happened within decades, possibly within years. That is extraordinarily fast for a planetary climate shift. Some researchers find that speed hard to explain with gradual processes alone. Others say gradual processes, given the right conditions, can produce sudden results. A system under pressure can hold for a long time and then tip quickly. A frozen river can hold back water for years and then break in a single afternoon. The world that existed during the Younger Dryas was not a slow, quiet world. It was a world under pressure, a world being pushed and pulled by forces that are still not fully understood. And the question of what finally broke it open and what was lost when it did is one that researchers are still sitting with. There is a kind of water that does not flow gently. It does not trickle down a hillside or wind through a quiet valley. It moves like something that has been held back for a very long time and has finally broken free. During the Younger Dryas, and in the strange, violent centuries just before it, water like that moved across the face of the earth, and the marks it left behind are still there, carved into stone and soil, waiting for someone to explain them. To understand what happened. It helps to picture the world as it was. Enormous sheets of ice covered much of the northern half of the planet. These were not ordinary glaciers. They were walls of frozen water, in some places more than a mile thick, pressing down on the land beneath them with unimaginable weight. And behind those walls, in the low places between the ice and the higher ground, water gathered. It pooled into lakes so large that some of them were bigger than any lake that exists today. One of the largest was called Lake Agassiz, a vast body of cold meltwater that sat along the southern edge of the great ice sheet in what is now North America. At its peak, it held more fresh water than all of the Great Lakes combined. For a long time, the ice held it in, but ice does not hold forever. When the edge of the glacier weakened, or when a channel opened through the ice, the water did not simply drain away. It burst. Researchers who study ancient floods call these events megafloods, and the word is not an exaggeration. Some of them may have released more water in a matter of weeks than the Amazon River carries in a year. The water tore across the land, carving channels hundreds of feet deep, stripping away soil, reshaping entire regions in a geological instant. In the American Northwest, there is a place called the Channeled Scablands. It is a strange, scarred stretch of land in what is now Washington State, cut through with enormous dry channels and dotted with giant ripple marks made of gravel. Each ripple is taller than a house. For a long time, geologists were not sure what had made them. Then a researcher named J. Harlan Bretz proposed, in the early 20th century, that a catastrophic flood had done it. His colleagues thought the idea was too extreme. Floods of that size, they said, simply did not happen. It took decades before the evidence became too clear to ignore. The channeled scablands were carved by floods from a glacial lake called Lake Missoula, which drained and refilled and drained again, possibly dozens of times over thousands of years. That story matters because it tells us something important. These floods were not rare, one-time events. They were part of a cycle. The ice would hold, the water would build, and then the barrier would fail, over and over again. The question that researchers are still working through is exactly how these floods connected to the Younger Dryas itself. One leading theory holds that a massive pulse of fresh water from Lake Agassiz poured into the North Atlantic Ocean around 12,800 years ago. Fresh water is lighter than salt water. When it floods into the ocean in enormous quantities, it can sit on top of the denser salt water and disrupt the great circulation system that moves heat around the planet. Some researchers believe this disruption is what triggered the sudden cold snap. The fresh water in this view acted like a switch, turning off the ocean's heat engine and plunging the northern hemisphere back into near glacial conditions almost overnight. But other researchers are not fully convinced. The timing is difficult to pin down precisely. Some studies of ocean sediments suggest the meltwater pulse may have happened slightly before the Younger Dryas began, which would fit the theory. Other studies find the evidence harder to read. The sediment record is not always clear, and some researchers argue that a single flood, even a very large one, may not have been powerful enough on its own to cause such a dramatic and lasting shift in global climate. So the question stays open. Was it the water that did it? Was the cold brought on by a flood so large it changed the ocean itself? Or were there other forces at work alongside it? Forces we have not yet fully measured or understood. The scars on the land are real. The carved channels are real. The giant ripple marks in Washington state are real. And they are still there, quiet and enormous under the open sky. They are evidence that something vast happened. They just have not told us everything yet. Somewhere around 12,000 years ago, the world was full of giants. Not in any mythic sense. Real animals, flesh and bone and weight. The kind of creatures that left deep tracks in soft ground and shook the earth a little when they moved through a forest. They had lived on this planet for hundreds of thousands of years. And then, in what feels like a very short time, most of them were gone. Picture a woolly mammoth. You may have seen drawings or models of one. Now hold that image and try to feel the scale of it. A full-grown mammoth stood about 13 feet tall at the shoulder. That is roughly as tall as a single-story house. Its tusks could reach 10 feet long, longer than most cars. It weighed somewhere between 6 8 tons. If you placed one on a modern scale, it would weigh as much as a large delivery truck loaded with cargo. These were not small animals living quietly at the edge of things. They were the landscape itself, moving and breathing. And they were not alone. North America was home to the giant ground sloth, which stood nearly 20 feet tall when it reared up on its hind legs. That is taller than a 2-story building. There was the short-faced bear, which could look a modern grizzly in the eye and still have height to spare. There was the American lion, bigger than any lion alive today. There was the glyptodon, a relative of the armadillo, but the size of a small car, covered in a dome of bony shell. There were horses and camels native to North America, long before European settlers brought their own. There were giant beavers the size of black bears. The word giant gets used so often that it starts to lose meaning. But these animals were genuinely, physically enormous in ways that are hard to fully picture. By about 10,000 years ago, most of them were gone from North America, gone from South America, gone from Europe and much of Asia. The extinctions happened across many continents in a relatively short window of time. That pattern is what makes researchers pause. The question of why is one of the most debated in all of paleontology, the study of ancient life. And the Younger Dryas sits right in the middle of that debate. One idea is that the cold itself killed them. The Younger Dryas dropped temperatures sharply and fast. The plants these animals depended on changed or disappeared. Grasslands shrank. Forests shifted. An animal that needs enormous amounts of food every day, and a mammoth needed to eat several 100 pounds of vegetation to survive, cannot simply adapt overnight when its food source vanishes. Some researchers point to the timing and say the climate shock alone was enough to push already stressed populations past the point of recovery. But there is a competing idea, and it has been argued just as passionately. Some researchers believe that humans hunted these animals to extinction. Early people arrived in the Americas during this same period. They were skilled hunters. The megafauna of the Americas had never encountered human hunters before, and the theory goes that they had no fear of us, no learned caution, they were easy prey. A small group of hunters, moving slowly across a continent over many generations, could have removed enough animals from enough populations to tip the balance. This idea is sometimes called the overkill hypothesis. It has supporters and critics in roughly equal measure. Critics point out that humans and mammoths coexisted in parts of the world for tens of thousands of years without driving them extinct. Supporters say the Americas were different, a new continent, naive animals, and a cold-stressed ecosystem all at once. Then there is the third possibility, which is that both things happened together. Climate stress weakened the populations. Human hunting finished them off. Neither cause alone would have been enough, but together they created a collapse. Some researchers find this the most persuasive reading of the evidence. Others say it is too convenient, a way of avoiding a firm answer by blaming everything at once, and then sitting quietly beneath all of these theories is the impact hypothesis. If something struck the Earth at the start of the Younger Dryas, if fires swept across the continent, if the skies darkened, if food chains broke apart all at once, then perhaps none of the simpler explanations are needed. Perhaps one event set everything else in motion. The honest answer is that no single explanation has closed the case. The bones are there. The dates are there. The cold is there in the ice. But the full story of why the giants vanished is still being written slowly, one fossil at a time. Imagine standing at the edge of a great forest. The trees rise tall around you, their bark dark with moisture, their canopy so thick that only thin ribbons of light reach the ground below. The air smells of pine and cold earth. Somewhere deeper in the woods, a branch cracks under the weight of snow. It is quiet. It is still. It feels like it has always been this way and always will be. Now imagine that forest simply stops. Not in a season, not over a century, but in what the geological record suggests was a remarkably short span of time, perhaps only a few decades. The trees pull back. The ground they once covered becomes open and pale. The soil hardens. The cold moves in like a slow tide, and where there was green and shadow, there is now something closer to tundra, flat, gray, and swept by wind. This is what the pollen record tells us happened across large parts of the northern hemisphere when the Younger Dryas began, roughly 12,800 years ago. Scientists study ancient pollen by drilling into the soft sediment at the bottom of lakes and bogs. Those sediments build up in layers over thousands of years, and each layer traps tiny grains of pollen from the plants that were alive at that time. The pollen grains are nearly indestructible. They survive long after the plants themselves are gone. And when researchers examine those layers under a microscope, they can read the history of an entire landscape, species by species, century by century. What those pollen records show at the Younger Dryas boundary is striking. In many parts of Europe and North America, the pollen from trees, oak, elm, hazel, birch, drops sharply. In its place, the pollen of cold-tolerant plants rises. Grasses, sedges, the low, tough plants that grow today in the far north, where the ground freezes solid for months at a time. The forests, it seems, retreated, and in some places they may have nearly vanished. One theory holds that the cooling was simply too fast for the forests to adapt. Trees are slow. They do not pick up and move. They spread by seed, and seeds need the right soil temperature, the right moisture, the right number of frost-free days to take root and grow. If the climate shifted faster than seeds could travel, the forests would have thinned and died at their northern edges without anything growing in to replace them. But there is a competing view. Some researchers suggest the picture was more complicated than a simple retreat. They point to evidence that certain tree species may have survived in small, sheltered pockets, valleys, south-facing slopes, places where the cold was slightly less severe. These refuges, as scientists call them, might have preserved small populations of trees through the worst of the cold. When the warmth eventually returned, those pockets could have been the source from which the forests spread again. The truth may lie somewhere between these two ideas, and the evidence is still being gathered. What is not in dispute is the visual transformation of the land. If you could have floated above Europe or North America during the heart of the Younger Dryas, the view would have been almost unrecognizable. Where dense woodland had stood, you would have seen open ground pale and wind-scoured. Permafrost, ground that stays frozen year-round, crept southward. In some regions, the soil itself may have shifted and cracked in the cold, forming the strange geometric patterns that frozen ground sometimes makes. Patterns that archaeologists still find preserved beneath modern fields. The rivers changed too, without tree roots holding the banks together. Rivers in some areas spread wide and shallow, braiding across open gravel plains rather than cutting deep channels through forested soil. The landscape became looser, more exposed, more raw. For the animals and people living through this, the loss of the forests was not just a visual change. It was the loss of shelter, of fuel, of food. The nuts and fruits that forests provide, the protection from wind, the cover for hunting, all of it thinned or disappeared in the coldest regions. Whatever communities of people existed in those latitudes would have had to move or adapt or find ways to survive in a world that looked nothing like the one their grandparents had known. The pollen record captures all of this in silence. Each tiny grain, no bigger than a speck of dust, holds the memory of a tree that once stood somewhere in a forest that is now long gone. The forests came back eventually, but what was lost in the years between, what people, what knowledge, what ways of living, that part of the record is far less clear. Somewhere beneath the surface of what we call history, there are people we can barely see. They left almost nothing behind. A few carved bones, a scatter of stone tools pressed into ancient soil, the faint ghost of a hearth, its ash long since dissolved into the earth. These were the people alive during the Younger Dryas, that long cold interval that gripped the planet roughly 12,800 years ago, and what their lives were actually like deep in that cold remains one of the quieter mysteries of human prehistory. We know they existed. That much the evidence confirms. Small bands of people moved across frozen plains and along the edges of retreating forests. They hunted animals far larger than anything alive today. They sheltered where they could. But the deeper question, the one that sits just below the surface of every archaeological dig from this period, is what that survival actually cost them. The cold was not just uncomfortable. Average temperatures in parts of the northern hemisphere dropped by as much as 10 to 15 degrees Celsius compared to the warmer period just before. That is an enormous shift. Winters would have been longer, harder, and darker than anything most of those populations had ever experienced. Food sources that had been reliable for generations suddenly became scarce or disappeared entirely. Some researchers think this period pushed certain human groups to the very edge of what a small population can survive. There is a concept in population biology called a bottleneck, which means a sharp reduction in the size of a group caused by some outside pressure. The group shrinks dramatically. Many individuals do not survive. The ones who do carry only a fraction of the genetic variety that existed before. Some researchers have looked at ancient DNA evidence, the genetic material recovered from old bones and teeth, and wondered whether the Younger Dryas created one or more of these bottlenecks in human populations across different parts of the world. The evidence is suggestive, but not settled. Other researchers argue the genetic signals we see could have come from earlier events or from migration patterns that have nothing to do with the cold snap at all. What makes this harder to answer is the problem of preservation. The Younger Dryas ended roughly 11,700 years ago. That is a long time for organic material to survive in the ground. Bone, wood, fiber, skin, all of it decays. What survives tends to be stone, and stone tells you only so much. It tells you someone was there. It tells you something about how they shaped their tools. It does not tell you how many of them there were, how long they stayed, or what happened to the ones who did not make it. Some sites from this period show a strange kind of thinning. The layers of human occupation, the strata that archaeologists read like pages in a book, become sparse or disappear entirely for stretches of time. One interpretation is that people simply moved on, following game or warmer conditions. Another interpretation is that some of those populations collapsed, leaving no one behind to leave a trace. Both ideas are plausible. Neither is proven. There is also the question of what people knew. these were not simple or unsophisticated minds. The people of this era were fully modern humans with the same cognitive capacity as anyone alive today. They had language, almost certainly. They had memory, tradition, and the ability to pass knowledge from one generation to the next. Some researchers wonder whether the trauma of the Younger Dryas, the sudden cold, the vanishing animals, the hunger, was encoded into cultural memory in ways that echoed forward for thousands of years. The flood stories, the tales of a lost golden age, the myths of a great catastrophe that ended an earlier and better world. Could any of those have roots in this period? That idea is speculative, and many archaeologists are cautious about it. Memory passed through oral tradition tends to distort over centuries, let alone millennia. What survives in myth may bear only a loose resemblance to whatever real event inspired it. The connection between the Younger Dryas and ancient flood narratives is an open question, not a conclusion, but the image stays with you. Small groups of people huddled against a cold that had no clear explanation, watching the world they knew grow harder and stranger with each passing year. They could not have known the cold would end. They could not have known that warmer centuries lay ahead. They only knew what was in front of them, which was ice and wind, and the long dark of a winter that seemed like it might never break. How many of them made it through, we cannot say with certainty. That the human line continued is obvious. How close it came to not continuing is a question the ground has not yet fully answered. There is a rhythm to human presence on this continent. It rises and falls like a slow tide. And around 12,800 years ago, something interrupted that rhythm in a way that researchers are still trying to understand. The people we call the Clovis were among the earliest well-documented inhabitants of North America. They left behind a very particular kind of stone tool, a long, carefully shaped spear point with a groove, called a flute, chipped into its base. These fluted points are beautiful objects. They are precise and deliberate. They speak of people who had mastered their craft over many generations. Clovis points have been found across a vast stretch of the continent, from the open plains to the eastern woodlands, scattered like seeds across the land. archaeological record, they almost disappear. The layer of earth that holds Clovis tools sits just below a thin, dark band that geologists call the black mat. This black mat is a layer of dark sediment found at dozens of sites across North America. Below it, Clovis tools and the bones of mammoths and other large animals appear together. Above it, those animals are largely gone, and the Clovis culture, as archaeologists recognize it, seems to fade from the record around the same time the Younger Dryas begins. What caused this? That question does not have a settled answer. One possibility is that the Clovis people simply adapted. Cultures shift, tools change. Some researchers think the people who came after the Clovis, groups who left behind different tool styles, known broadly as post-Clovis cultures, were the same people or their descendants who had simply changed the way they worked stone in response to a changing world. On this view, there is no disappearance at all. There is only transformation. But other researchers look at the timing and find it hard to ignore. The Younger Dryas arrived suddenly. The megafauna, the mammoths, the mastodons, the giant ground sloths were vanishing. The forests were changing. The grasslands were shifting. The world that the Clovis people had known was reorganizing itself within a single human lifetime. It would be strange if that left no mark on the people living through it. This is where the rhythm becomes visible. Human cultures in the deep past seem to pulse in response to the climate. When conditions are stable and food is plentiful, populations grow and spread. When conditions shift sharply, populations contract, fragment, and sometimes vanish from regions they once occupied. This is not unique to North America. It appears in the record on nearly every continent. The climate breathes, and human presence breathes with it. The Younger Dryas was one of the sharpest of those breaths. Some researchers point to the black mat itself as a clue. The dark color and unusual chemistry of this layer have led certain scientists to propose that it formed in the aftermath of a catastrophic event, possibly a large fire or a sudden change in soil conditions, or something more dramatic still, the impact hypothesis, which we will sit with more fully in a later section, suggests that a fragment of a comet or asteroid may have exploded over the ice sheet, triggering fires and a rapid cooling. If that is true, the black mat might be a kind of scar left by that event. But the black mat interpretation is contested. Other researchers argue that the layer formed through more ordinary processes, changes in water flow, shifts in vegetation, the slow accumulation of organic material in a cooling climate. They point out that similar dark layers appear in many places where no impact evidence has been found. The debate over what the black mat means is ongoing. What is harder to argue with is the silence. The Clovis tool tradition, so widespread and so recognizable, simply stops appearing after a certain point. Whatever came next was different. Whether that difference reflects survival and adaptation, or collapse and replacement, or something in between, remains genuinely open. There is something quietly moving about holding one of those fluted points in the mind's eye. Someone made it with great care. They knew exactly what they were doing. They lived in a world that was about to change in ways they could not have imagined. And then the record goes quiet, the way a fire goes quiet when the last log burns down to coals. The rhythm of human presence on this continent did not end, but it changed. Something interrupted the pulse. And what that something was, and what it cost the people living through it, is a question the stones have not yet fully answered. Something changed in the soil around 12,800 years ago. Not just in one place, not just in one forest or one valley. Something changed across a wide stretch of the continent, and the evidence for it is thin and dark and strange. It is a layer of burned material, buried just below the surface of the earth, found at dozens of sites spread across North America and parts of Europe. Researchers call it the black mat. It is a thin band of dark sediment, almost like a stripe pressed into the ground. Below it, the bones of mammoths and horses and giant sloths. Above it, almost nothing. The black mat sits at the boundary of the Younger Dryas. That much is agreed upon. What caused it is not. Some researchers look at this dark layer and see fire, not the ordinary kind, not a campfire or a lightning strike in a dry meadow. They see evidence of burning on a scale that is hard to picture. Charcoal particles, soot, tiny glass-like beads called microspherules, which form when material is heated to extreme temperatures and then cools very quickly. These beads have been found at multiple sites, all roughly the same age. The question is what made them. One idea is that massive wildfires swept across the continent at the start of the Younger Dryas. The climate was shifting fast. Forests were drying. Grasslands were changing. A series of large fires, perhaps sparked by drought or by some other cause, could have left behind exactly this kind of layer. Fire leaves charcoal, fire leaves ash, and fire on a large scale can reshape an ecosystem for centuries. But some researchers are not satisfied with ordinary fire as an explanation. They point to the microspherules. They point to tiny grains of a mineral called nanodiamonds, which can only form under conditions of enormous heat and pressure. They point to elevated levels of platinum and iridium, metals that are rare in ordinary rock, but more common in objects that fall from space. These researchers argue that the burning was not caused by drought or lightning. They argue it was caused by something arriving from outside the atmosphere entirely. This is the edge of the impact hypothesis, which the next part of this story will sit with more carefully. But here in this section, what matters is the fire itself, because fire does not stay in one place. Fire moves. Fire changes what lives and what does not. And the evidence of burning at the start of the Younger Dryas is not a single point on a map. It is spread across a wide area, from the American Southwest to the Great Lakes region, with echoes found in sites in Europe and the Middle East as well. Other researchers push back on this picture. They argue that the black mat is not as widespread or as uniform as the impact supporters suggest. They point out that charcoal layers can form from many causes over many years. They note that some of the chemical signatures, like the platinum spikes, are present at some sites, but absent at others. If a single event caused all of this, the evidence should be more consistent. The fact that it is not, they say, suggests something more complicated. Perhaps many smaller events. Perhaps regional fires with different causes. Perhaps the black mat is not one story, but many stories pressed together by time. What is harder to argue with is the effect. Whatever caused the burning, the world on the other side of that dark layer was different. The animals that had lived below it were mostly gone. The plant communities had shifted. The humans who had been moving through these landscapes were fewer or quieter, or had moved somewhere else. The Clovis culture, which left its distinctive stone tools across North America, seems to fall silent right around this boundary. Whether fire was the cause, or just one part of a larger collapse, is still an open question. There is something quietly unsettling about a stripe of black in the earth. It does not shout. It does not announce itself. It just sits there, pressed between layers of older soil and newer soil, holding whatever it holds. Researchers dig carefully around it. They take samples. They measure and compare. And they argue politely and persistently about what it means. The fires may have been vast. They may have been scattered and local. They may have been part of something larger arriving from above, or they may have been the Earth's own response to a climate spinning out of balance. The dark layer does not say. It only holds the ash, quiet and patient, waiting for someone to ask the right question. There is a theory about the Younger Dryas that sits at the very edge of what science can confirm. It is not settled. It is not dismissed. It lives in that uncomfortable space where the evidence is real, but the explanation remains deeply contested. And it may be the most extreme idea in this entire story. The theory goes like this. Around 12,800 years ago, something struck the earth, or perhaps many somethings. A comet, or a cluster of fragments from a comet, may have broken apart in the upper atmosphere and rained fire across a wide stretch of the northern hemisphere. Not a single clean crater, not one obvious scar, something more diffuse, more scattered, and in some ways more difficult to prove. The researchers who support this idea call it the Younger Dryas impact hypothesis. They point to a thin layer of material found at dozens of sites across North America, Europe, and the Middle East. This layer sits right at the boundary, the precise moment in the geological record where the warm world ended and the cold came came rushing back. Inside that layer, they have found things that are very hard to explain any other way. One of those things is platinum. Platinum is rare on the Earth's surface. It is far more common in space rocks, in meteorites and comets that drift through the solar system. When scientists find an unusual spike of platinum in a sediment layer, it raises a question. Where did it come from? Some researchers argue that the platinum spikes found at Younger Dryas boundary sites are a fingerprint, a sign that something from space arrived here and left its mark in the soil. There are also tiny spherules, small, perfectly round beads of glass and carbon found in that same layer. These spherules form when rock or soil is heated to extreme temperatures almost instantly. The kind of temperatures that occur during an impact event or when a comet fragment explodes in the lower atmosphere. Some of these spherules contain a form of carbon called nanodiamonds. Nanodiamonds require enormous pressure and heat to form. They do not appear naturally in ordinary sediment. Their presence in this layer is one of the more striking pieces of evidence the impact theorists point to, and yet the critics are not quiet. Many geologists and archaeologists push back hard on this hypothesis. They argue that the platinum spikes could have other sources. Volcanic activity, for instance, can concentrate rare metals in unusual ways. The spherules, some say, could have formed through wildfires rather than impacts. The nanodiamonds have been disputed too. Some researchers have struggled to replicate the original findings, which is a serious concern in science. When one laboratory finds something and another cannot confirm it, the question stays open. The critics also point to something fundamental. There is no confirmed crater from this event. A comet large enough to trigger a global climate shift should leave some kind of physical scar on the landscape. The impact theorists respond that a comet exploding in the atmosphere rather than striking the ground directly might not leave a traditional crater. They point to the 1908 Tunguska event in Siberia, where a space rock exploded miles above the ground and flattened a vast forest without leaving a crater at all. Something similar, they suggest, but far larger, could explain the Younger Dryas boundary layer without a visible impact site. What makes this theory so extreme is the scale it implies. If a comet or comet cluster did break apart over the northern hemisphere 12,800 years ago, the fires it ignited could have been enormous. Some researchers estimate that vast areas of forest and grassland burned within a very short period. The smoke and debris thrown into the atmosphere could have blocked sunlight. Cooler temperatures would follow. Ice sheets that were already melting might have slowed or halted. The whole fragile warming trend of the late Ice Age could have been interrupted in a matter of years, or even months. That is an almost incomprehensible speed for a climate event. The Earth is used to slow change. Ice ages build over thousands of years. But the Younger Dryas, as the ice cores show, began with startling speed, and a comet impact is one of the few forces that could explain that speed. The debate continues in the scientific literature. New sites are found. New measurements are taken. Some studies support the impact layer. Others challenge it. The question of what caused the Younger Dryas remains genuinely open, and the impact hypothesis remains one of the most extreme and contested answers anyone has proposed. A scar in the sky, a layer in the soil, and a world that changed almost overnight. Somewhere beneath the surface of the ocean, something moves. It moves slowly. It moves silently. And for most of human history, no one knew it was there at all. It is called the thermohaline circulation. That is a long name for a simple idea. Therma means heat. Haline means salt. Together, they describe a vast system of currents that carries warm water north and cold water south, looping through every ocean basin on Earth like a slow, enormous river with no banks. Some researchers call it the ocean conveyor belt, because that image captures something true about it. It is always moving. It is always carrying. And when it slows down, the whole planet feels it. Here is how it works, in the quietest possible terms. Warm water from the tropics flows north along the surface of the Atlantic Ocean. As it travels, it releases heat into the air above it. That heat drifts east, and it warms the lands of northern Europe. Without it, places like Iceland and Norway would be far colder than they are. The current is, in a very real sense, a slow-moving heater for the northern world. But the current does not just carry warmth. It also carries salt. As the warm water moves north and releases its heat, it cools. Cold water is denser than warm water. Salty water is denser than fresh water. So this cold, salty water grows heavy. It sinks. It drops down into the deep ocean and begins a long, slow return journey south along the ocean floor. That sinking is the pump. That is the engine that keeps the whole system running. And during the Younger Dryas, something may have broken that pump. The leading idea, the one that many researchers have spent decades examining, is that a sudden flood of fresh water poured into the North Atlantic. Fresh water is lighter than salt water. If enough of it entered the ocean at once, it could have floated on the surface like a lid, preventing the warm, salty Atlantic water from cooling and sinking. Without that sinking, the pump would stall. The conveyor would slow or stop, and the heat that had been flowing north would no longer arrive. The result, in theory, would be a rapid and dramatic cooling across the northern hemisphere. Temperatures in some regions may have dropped by several degrees within decades, or perhaps even faster. The evidence from Greenland ice cores suggests the change was startling in its speed. Some estimates place the cooling at 10 degrees Celsius or more over a very short span of time. That is not a gradual shift. That is something closer to a door swinging shut. What makes this section of the story so quietly remarkable is the mechanism itself. The ocean conveyor is not dramatic. You cannot see it from a shoreline. You cannot hear it. It leaves no visible mark on the landscape. And yet, it may be one of the most powerful forces shaping the climate of the entire planet. The idea that something so invisible, so slow, so subtle, could be responsible for one of the most severe climate events in human prehistory is genuinely strange to sit with. The competing question, and it is a real one, is what caused the fresh water pulse in the first place. One prominent theory points to Lake Agassiz, a vast glacial lake that sat over much of what is now central Canada. It held an almost unimaginable volume of meltwater. Some researchers believe it drained catastrophically into the North Atlantic, flooding the ocean with enough fresh water to disrupt the Conveyor. But the precise timing of that drainage is still debated. Not everyone agrees it happened at exactly the right moment to trigger the Younger Dryas. Others have proposed that the meltwater came not from a single lake, but from multiple sources, draining gradually over time. Still others wonder whether the Conveyor was already weakening before any flood arrived, and whether some other force, perhaps the impact event discussed in earlier sections, delivered the final disruption. The honest answer is that no single explanation has yet closed the question. What remains is this quiet image: a vast, invisible river moving through the deep ocean. Salt and temperature working together like gears in a machine no one can see. And somewhere in the cold record of ancient ice, a signal that says, the pump slowed, the heat stopped arriving, and the world grew cold again. The ocean still runs that Conveyor today. The pump still works, as far as researchers can tell. But the question of how fragile it might be and what it would take to slow it again remains genuinely open. Tonight, somewhere far below the surface of the Atlantic, cold water is sinking. Slowly, silently, carrying the memory of a much older cold. There is a lake that no longer exists. It was once one of the largest bodies of fresh water the world has ever held. At its peak, it covered more land than all of today's Great Lakes combined. It sat heavy and cold across what is now central Canada, pressed down by its own enormous weight. And for a long time, no living person knew it had ever been there at all. The story of how we found it begins in the 19th century with a Swiss-born scientist named Louis Agassiz. He was a geologist and naturalist who spent years studying the landscapes of Europe and North America. He noticed something strange about the land. Enormous boulders sat in places where no river or stream could have carried them. The bedrock beneath his feet was scratched and grooved in long parallel lines. These were not the marks of wind or rain. Something much heavier had moved across the surface of the earth. Agassiz proposed an idea that most of his colleagues found difficult to accept. He suggested that great sheets of ice had once covered vast portions of the northern world. These glaciers, he argued, had dragged boulders across the land and carved those deep grooves into solid rock. He called this the Ice Age. The scientific community resisted at first. The idea seemed too large, too strange, but the evidence kept accumulating, and slowly the theory took hold. Decades later, geologists began to look more carefully at the flat, lake-bed sediments spread across the Canadian prairies. The land there was unusually level. The soil had a particular layered quality, the kind that forms at the bottom of still water. Researchers began to piece together a picture of an ancient lake, enormous and cold, that had pooled behind the retreating glaciers as the last ice age wound down. They named it Lake Agassiz in honor of the man who had first helped the world see ice as a force of history. But naming the lake was only the beginning. The harder question was what had happened to it. A lake that large does not simply evaporate. It goes somewhere. And when geologists began to trace the ancient drainage channels, the story grew more complicated and more strange. The leading hypothesis is that Lake Agassiz drained catastrophically, not slowly over centuries, but in a sudden and enormous release of cold, fresh water into the North Atlantic Ocean. The idea is that the ice dam holding the lake in place gave way, perhaps all at once, and billions of gallons of cold meltwater poured eastward through what is now the St. Lawrence River Valley. Some researchers estimate this flood may have been one of the largest single releases of fresh water in the last 20,000 years. This is where the cold flood hypothesis connects to the Younger Dryas. The theory holds that this massive pulse of cold, fresh water disrupted the ocean's circulation system. Fresh water is lighter than salt water. When it floods into the ocean in enormous quantities, it can sit on the surface and prevent the normal sinking and mixing that drives the great ocean currents. If the Atlantic circulation slowed or stopped, the warmth it normally carries northward would have been cut off, and the climate, which had been warming steadily, would have plunged back into cold. It is a compelling idea, but it is not without its problems. Some researchers have struggled to find clear geological evidence of a single catastrophic flood at exactly the right time. The sediment record is incomplete in places. Dating the precise moment of the drainage is difficult. One competing view holds that the lake may have drained in multiple smaller pulses over a longer period, rather than in one sudden event. If that is true, the mechanism for triggering the Younger Dryas becomes less clear. Other researchers point out that the cold snap may have begun slightly before the most likely timing of the Lake Agassiz flood. If the climate was already cooling when the flood occurred, then the flood may have deepened or extended the cold rather than caused it. The question of cause and effect remains genuinely open. What is not in doubt is that Lake Agassiz was real. The evidence of its existence is written in the land itself. In the flat sediment plains, the ancient shorelines etched into hillsides, the river channels carved far too wide for the modest streams that run through them today. The lake was there. It drained. The world changed. How exactly those three things connect is still a question that geologists and climate scientists are working to answer. The lake left its mark on the land. Whether it also left its mark on the climate and on the people who lived through what followed is a thread that has not yet been fully traced. There is something strange to sit with as you close your eyes tonight. The world you know, its coastlines, its shallow bays, its river mouths opening to the sea, is not the world that existed 12,000 years ago. The edges of the continents looked different then. Quite different. And the reason why is one of the quieter surprises hiding inside the story of the Younger Dryas. During the last great ice age, enormous amounts of water were locked up in glaciers and ice sheets. So much water, in fact, that the global sea level was roughly 120 meters lower than it is today. 120 meters. That is taller than a 40-story building. The ocean had pulled back from the land like a slow tide retreating, exposing vast plains of coastal shelf that are now completely underwater. These were not barren wastelands. They were living land. Forests grew there. Rivers crossed them. Animals grazed on them. And almost certainly, people walked across them. The continental shelves, those wide, gently sloping underwater ledges that ring the continents, were dry ground, habitable ground, ground that people may have called home for thousands of years. Then the ice began to melt, and the sea came back. The rise was not even or gentle. Some researchers believe it happened in pulses, sudden surges of meltwater that lifted sea levels by several meters in a matter of centuries, or possibly even decades. One such event, called Meltwater Pulse 1A, may have raised sea levels by as much as 15 to 20 meters in a geologically brief span of time. The timing of this pulse is still debated. Some place it before the Younger Dryas. Others suggest the cold period itself interrupted the melting, and that when the warming returned at the end of the Younger Dryas, the seas surged again. What this means is that entire coastlines, entire inhabited regions were drowned, not in a single dramatic moment, but over generations, over lifetimes, over the slow accumulation of years in which the water crept higher and the land shrank. Beaches became shallow water. Shallow water became open sea. The world that people had known, the world their grandparents had walked on, simply disappeared beneath the waves. Here is the counterintuitive part. Because these coastal areas were so productive, warm, sheltered, rich in fish and shellfish and fresh water, they were likely among the most densely populated places on Earth at the time. Coastal living has always drawn people. The food is reliable. The climate is mild. The water provides. So the regions most likely to have supported large, settled human communities were precisely the regions that the rising sea swallowed whole. Whatever those communities built, whatever they remembered, whatever they left behind, most of it is now sitting under tens of meters of ocean. And we have barely looked. Some researchers point to this as a significant gap in the archaeological record. The evidence we have for early human life tends to come from inland sites, from caves, from high ground that stayed dry. But if the richest, most populated areas were coastal, then we may be missing a large portion of the story. The absence of evidence is not evidence of absence, as the saying goes. It may simply be evidence of depth. A few intriguing finds have come from underwater surveys off the coasts of India, in the Persian Gulf, in the North Sea, and along the edges of North America. Researchers have found submerged stone tools, ancient hearths, and the bones of land animals in places that are now well below the waterline. These finds confirm that people did live on what is now seafloor. But the surveys are expensive and difficult, and only a small fraction of the drowned shelf has ever been examined closely. The competing view is that while these coastal areas were certainly inhabited, they were inhabited by small, mobile groups of hunter-gatherers who left little permanent trace, even on dry land. The loss of these coastlines in this view was a human tragedy, but not the erasure of a complex civilization. The evidence for large, settled coastal societies before the Younger Dryas simply does not yet exist. And that is the quiet tension at the heart of this question. The absence of evidence could mean there was nothing remarkable to find. Or it could mean the remarkable things are still down there, resting in the cold dark of the continental shelf, waiting for someone to look. The sea keeps its secrets well. It always has. And the drowned coastlines of the Younger Dryas may be holding more of our history than we have yet imagined. We simply do not know. Not yet. There is a site in southern Turkey, buried under centuries of soil and wind-blown dust, that should not exist. Its stones are massive. Its carvings are careful and deliberate. Its pillars stand in careful circles, shaped by human hands into forms that suggest ritual, meaning, and organized effort. The site is called Göbekli Tepe, and the date carved into its existence by archaeologists is roughly 12,000 years ago, right at the edge of the Younger Dryas, right at the boundary between the deep freeze and the slow return of warmth. That date is the problem, or rather, it is the question. Everything we thought we understood about early human civilization said that people at that time were small groups of wanderers. They followed animals. They gathered plants. They had no cities, no temples, no organized labor on a grand scale. The standard picture was one of scattered bands, moving quietly across a cold and difficult world. Then Göbekli Tepe appeared from beneath the earth, and that picture became harder to hold. The pillars at Göbekli Tepe are tall, some nearly 6 meters high. They weigh many tons. Moving them required coordination. Feeding the workers who moved them required a food supply that did not simply wander past. Some researchers look at this and wonder whether a more organized society existed before the one we thought came first. Others push back firmly. They argue that complex ritual sites do not require cities or agriculture. Hunter-gatherer groups, they say, can organize around shared belief and seasonal gathering. The stones prove community, not civilization in the full sense of the word. Both views sit with the evidence. Neither one fully explains it. What makes Göbekli Tepe feel connected to the Younger Dryas is its timing. The site was built during or just after one of the most violent climate disruptions in human memory. The world around it was cold, stressed, and changing. Coastlines were different. Forests had retreated. The animals people depended on were disappearing. And yet, here were people cutting stone and raising pillars in careful geometric arrangements. The question some researchers quietly ask is whether this kind of organized effort was new, or whether it was a continuation of something older, something that had existed before the cold came back and then survived it. That older something, if it existed, would be very hard to find. The Younger Dryas ended roughly 11,700 years ago. Sea levels rose significantly in the centuries that followed. Coastlines that had once been dry land went underwater. Any settlements built near the sea during the cold period, when sea levels were lower, would now sit beneath tens of meters of ocean. The drowned coastlines discussed earlier in this story are not just a geological curiosity. They are also a kind of archive, sealed away from us. Some researchers point to flood myths as a faint echo of this lost world. Cultures across the globe carry stories of a great flood, a sudden rising of water, a world swallowed by the sea. The Black Sea, which some geologists believe flooded catastrophically as the ice sheets melted, sits near the region where some of the oldest known agricultural settlements appeared. Whether that flooding and those stories are connected is genuinely unknown. The myths are real. The flood may be real. The link between them is still an open question. What ties all of this together? Göbekli Tepe, the drowned coasts, the flood stories, the sudden end of the Younger Dryas, is a web of timing. Everything clusters around the same few thousand years. The cold breaks, the seas rise, the megafauna vanish, and then, almost abruptly, organized human settlements begin to appear in the archaeological record. Agriculture spreads. Pottery appears. Villages grow into towns. One possibility is that the Younger Dryas itself was the pressure that forced this change. Stress, some researchers suggest, drives innovation. A cold, difficult world may have pushed human groups to cooperate in new ways, to store food, to plan across seasons rather than just days. The organized effort at Göbekli Tepe may be a product of that pressure, not evidence of something that came before it. Another possibility is that we are only seeing the survivors. Whatever existed before the cold, before the floods, before the rising seas, most of it is gone. What we call the beginning of civilization may simply be the earliest layer that survived long enough for us to find. The stones at Göbekli Tepe do not answer this. They only stand there, patient and worn, in the dry hills of southern Turkey, waiting for a question we have not yet learned how to ask. When the cold came back 12,800 years ago, the world did not freeze all at once. It shifted. It tilted. Some creatures bent with it. Some did not. And the question of why certain animals survived while others vanished is one that researchers are still quietly turning over, like a stone found in an unexpected place. Before the Younger Dryas, the great Megafauna, the enormous animals that had walked the earth for tens of thousands of years, were already under pressure. Woolly mammoths moved across the cold grasslands of the north. Giant ground sloths, some as tall as small trees, grazed across the Americas. Mastodons, which looked something like elephants, but were a distinct and separate lineage, browsed through forests and wetlands. Cave lions and short-faced bears, animals of a size that is hard to imagine now, roamed territories that stretched for hundreds of miles. Then the cold returned, and within a few thousand years, most of them were gone. the question is not simply that they disappeared. Many large animals have come and gone across deep time. The question is the timing. The losses cluster around the end of the Younger Dryas, and the chaotic centuries just before and after. That clustering is what makes researchers pause. It suggests something more than ordinary change. One line of thinking points to human pressure. By the time the Younger Dryas ended, people had spread across nearly every continent. They were skilled hunters. Some researchers argue that even small, steady hunting pressure on large, slow-reproducing animals could push a population past a tipping point. A mammoth, for instance, likely took many years to reach maturity and produced only one calf at a time. A modest increase in hunting deaths, year after year, could quietly hollow out a population before anyone noticed the numbers falling. But other researchers are not satisfied with that explanation alone. They point out that humans and mammoths had shared the same landscapes for tens of thousands of years before the extinctions. If hunting pressure alone were enough, why did the collapse happen when it did, and not earlier? The timing still needs explaining. A second line of thinking focuses on habitat. The Younger Dryas reshaped the land in ways that were not easy for large animals to absorb. The cold, dry grasslands that mammoths depended on, sometimes called the mammoth steppe, shrank as temperatures fluctuated and then warmed. Forests moved in where open ground had been. The food that sustained enormous herds became patchy and unreliable. Some researchers believe the habitat loss was the primary driver, with human hunting adding a final, quiet pressure to populations already struggling. There is also the question of what happened to the animals that did survive. Bison survived, though they shrank in body size over the following millennia. Elk survived. Wolves survived. Some researchers find this pattern puzzling. If the cold or the warming or the disruption was severe enough to kill mammoths, why did bison come through? One possibility is that bison were more flexible in their diet and could adapt to a wider range of plant communities. Another is that their reproductive rate was simply faster, giving populations more room to recover from losses. The honest answer is that no single explanation fits all the survivors and all the losses neatly. The impact hypothesis, which proposes that a comet or fragmented object struck or exploded over the Earth near the start of the Younger Dryas, adds another layer to this question. Some researchers who support that hypothesis suggest the event would have caused fires, dust, and a sudden loss of food sources severe enough to push already stressed populations over the edge. The platinum and other chemical markers found at certain sites around the world are offered as evidence that something unusual happened in the atmosphere and on the ground at roughly this time. Critics of the hypothesis argue those markers can have other explanations, and that the evidence is not consistent enough across sites to point clearly to a single catastrophic event. What is clear is that the world that emerged from the Younger Dryas was a quieter one in terms of large animals. The great herds were gone or reduced. The predators that had depended on them faded too. The land held the same soil, the same rivers, the same mountains, but the creatures moving across it were smaller, fewer, and different. Some researchers wonder whether the loss of those large animals itself changed the land in ways that still echo today. Large grazers shape vegetation. They compact soil. They move seeds. Their absence may have altered entire ecosystems in ways that are still unfolding, slowly and without announcement, across the long centuries since the cold finally let go. There is a kind of light that only very old stone can hold. Stand near a piece of ancient carved rock on a clear morning, and you will notice it. The surface catches the low angle of the sun differently than the ground around it. The shadows fall into the grooves in a way that seems almost deliberate. The stone glows faintly, as if it has been waiting a long time for someone to look. At a site called Göbekli Tepe, in what is now southern Turkey, there are stones like that. They are enormous. Some of the carved pillars stand nearly 6 meters tall and weigh more than 10 tons. They were shaped and raised by human hands at least 12,000 years ago, possibly earlier. That places their construction right at the edge of the Younger Dryas, or just after the cold finally began to ease. And no one is entirely sure why they were built. The carvings on those pillars are worth sitting with for a moment. There are animals cut into the stone with real skill. Foxes, cranes, scorpions, wild boars. Some researchers believe the carvings record something about the sky, about the positions of stars at a particular moment in time. One hypothesis, still debated and far from settled, suggests that certain arrangements of the carved animals may correspond to a specific night sky from around 12,800 years ago, which is roughly when the Younger Dryas began. The idea is that someone or some group of people wanted to remember something that happened. They carved it into stone so it would not be forgotten. That is a striking thought, but it is only a hypothesis. Other researchers look at the same carvings and see something else entirely. They see ritual symbols or representations of local wildlife or images tied to beliefs about death and the spirit world. The carvings are real. What they mean is genuinely open. What makes Göbekli Tepe so difficult to place in the story of the Younger Dryas is that it should not exist at all by the older models of human history. For a long time, the accepted view was that complex architecture came after farming. First, people settled down, grew crops, built villages, and then, eventually, built monuments. Göbekli Tepe reverses that sequence. The people who built it were, as far as the evidence shows, still hunter-gatherers. They had not yet domesticated wheat. They were moving with the seasons. And yet, they organized the labor to raise these massive carved pillars in precise arrangements. Some researchers wonder whether the trauma of the Younger Dryas or the memory of whatever catastrophe preceded it drove early humans toward new kinds of gathering. Perhaps shared ritual, shared building, shared stone became a way of holding a community together when the world had become cold and strange and frightening. The monument on this reading is a kind of answer to chaos. Others are more cautious. They point out that we have only a fraction of the site excavated. Most of Göbekli Tepe is still underground. What we have found may be only the outermost edge of something much larger and more complex. The full picture, whatever it is, has not yet come to light. There is another kind of ancient memory worth considering here, and it too involves light in a quiet way. Across many cultures, there are old stories about a great darkness, a time when the sun seemed to dim or disappear, when fire fell from the sky, when the world was remade by flood and cold. These stories come from places very far apart. They do not all describe the same event, but some researchers notice that a surprising number of them cluster around a similar theme. A world that was warm and full, then suddenly was not. Oral traditions can carry memory across many generations. Some studies of indigenous Australian stories suggest that certain spoken accounts may preserve accurate descriptions of coastline changes that happened thousands of years ago. If that is true, then the spoken word can hold geological time inside it. The question is whether any of the flood and fire stories from the end of the Younger Dryas period carry real memory of real events, or whether they are simply the kinds of stories that human minds tend to generate when they try to explain a difficult world. That question has no clean answer yet. The light on old stone, the carvings of animals in careful rows, the stories passed down through uncountable generations of human voices. All of it points toward something. What that something is remains, for now, beautifully unclear. The stones hold their shapes. The shadows move across them as the sun travels. And the question of what was remembered and why stays open in the quiet dark. There is a sound that glaciers make when they begin to die. It is not a gentle sound. It is not the soft drip of a faucet or the quiet trickle of a stream. It is something much larger. A deep, low groan that travels through ice and stone and water all at once. Scientists who work near glaciers today describe it as a kind of moaning, a vibration you feel in your chest before you hear it with your ears. The ice is under pressure. It is shifting. And when it finally gives way, the sound is enormous. Imagine that sound stretched across an entire continent, across thousands of miles of ice sheets, all beginning to soften at once. That is something close to what the end of the Younger Dryas may have sounded like, if anyone had been standing close enough to hear it. The warming that ended the Younger Dryas came quickly. the ice cores from Greenland, those long cylinders of ancient frozen air that scientists drill up from deep below the surface, suggest that temperatures in parts of the northern hemisphere rose by as much as 10 degrees Celsius in just a few decades. Some researchers think the shift was even faster than that. A few decades is nothing in geological time. It is barely a breath. And yet the world that emerged on the other side of that warming was almost unrecognizable compared to the world that had existed just before. This kind of rapid shift is sometimes called climate whiplash. The term captures something real. The planet had been locked in cold for roughly 1,200 years. Then, around 11,700 years ago, the cold broke. The ice began to retreat. The great sheets that had covered much of North America and Northern Europe started pulling back toward the poles. Rivers swelled. Coastlines shifted. Forests began to creep northward into land that had been frozen tundra for generations. But what caused the warming to arrive so suddenly? That question is still open. One leading idea points to changes in the ocean circulation system. During the Younger Dryas, the flow of warm water through the North Atlantic had slowed dramatically. Some researchers believe it nearly stopped. When that circulation began to recover, perhaps as the flood of cold meltwater that had disrupted it finally dispersed, warm water started moving north again. The ocean acted like a furnace being switched back on. Heat returned to the high latitudes. Ice began to melt, and the feedback loops that drive climate, where warming causes melting, which causes more warming, began to spin in the opposite direction from the ones that had caused the freeze. A competing idea is that the trigger was not the ocean at all, but the sky. Some researchers point to shifts in Earth's orbit and the angle at which sunlight strikes the northern hemisphere. These orbital cycles change slowly over thousands of years, and some calculations suggest that by around 12,000 years ago, the northern hemisphere was receiving slightly more solar energy during summer months. That extra warmth, even if small, may have been enough to tip the balance. The ocean circulation may have recovered as a result, rather than being the cause. Both ideas have evidence behind them. Neither fully explains the speed of the change. And the speed is what keeps drawing researchers back to this question. Even if orbital shifts and ocean circulation can explain why the warming happened, they struggle to explain why it happened so fast. Some scientists wonder whether there was a trigger, something sudden that pushed the climate system past a threshold it had been approaching for years. What that trigger might have been remains one of the genuinely open questions of this period. The sounds of that transition would have been everywhere. The crack of ice shelves breaking apart, the rush of meltwater pouring into rivers and bays, the low rumble of land rising, because land actually rises when the weight of ice is removed from it, slowly at first, then faster. A process called isostatic rebound. The ground itself was moving. The coastlines were changing. The world was, in a very physical sense, groaning back to life. For the people who lived through it, the change must have been both a relief and a disruption. The cold had been brutal, but the warming brought its own upheavals. Floods, shifting food sources, coastlines that swallowed familiar places beneath rising water. What those people made of all this, what stories they told, what sounds they heard in the ice and the rivers and the rising seas, we can only wonder. The warming came. The world changed. And the questions it left behind are still with us, quiet and open, like the last echo of a sound too large to fully hear. There is a kind of quiet mathematics hidden inside the story of the first farmers. It does not announce itself. It does not arrive with fanfare. It simply sits inside the numbers, patient and strange, waiting for someone to look closely enough to notice it. Consider the timing. The Younger Dryas ended roughly 11,700 years ago. Within a few thousand years of that ending, something remarkable happened in a handful of places scattered across the world. People began to plant seeds on purpose. They began to tend the soil. They began to stay in one place and wait for the earth to give something back. Researchers call this the Neolithic transition, the shift from wandering and gathering to settling and growing. And the timing of it, when you lay it against the climate record, is striking. The warming that closed the Younger Dryas was not gradual. The ice cores from Greenland suggest temperatures in that part of the world rose by something close to 10 degrees Celsius in perhaps a decade or two. That is an enormous shift in an almost impossibly short span of time. And then, within a geological blink after that warming stabilized, the first signs of deliberate cultivation appear in the archaeological record. Wheat and barley in the Fertile Crescent, rice along the Yangtze River Valley, squash and maize in Mesoamerica. The numbers cluster. The timing rhymes. Some researchers find this clustering too tidy to be coincidence. One idea is that the end of the cold period simply unlocked conditions that made farming possible: warmer temperatures, more reliable rainfall, longer growing seasons. On this view, the math is not mysterious at all. It is just cause and effect. The climate opened a door, and people walked through it. But other researchers push back gently on that explanation. They point out that anatomically modern humans had lived through warm periods before. There were interglacials, long stretches of relative warmth, going back hundreds of thousands of years. People did not begin farming during those earlier warm spells. Something about this particular warming at this particular moment seems to have been different. The question of why remains genuinely open. One possibility involves population pressure. During the Younger Dryas, cold and dry conditions may have pushed human groups into tighter spaces near reliable water sources. When the warming came, those groups were already concentrated in fertile river valleys and coastal lowlands. The seeds they had been collecting for generations were already in their hands. The soil was already beneath their feet. Perhaps the mathematics of survival simply reached a threshold, and farming was the answer that emerged. Another possibility is more subtle. Some researchers wonder whether the cognitive and social tools needed for farming, the ability to plan across seasons, to store surplus, to organize labor across a community, had been quietly developing for tens of thousands of years. And the end of the Younger Dryas was simply the moment when all those pieces finally aligned. On this view, farming was not invented so much as it was finally attempted by people who were already ready. There is also the question of what was lost. if there were earlier communities with some degree of settled life, communities that the Younger Dryas itself may have scattered or erased, then what looks like the beginning of farming might actually be a recovery, a rebuilding. The numbers we see in the record might represent not the first attempt, but a later one. That idea remains speculative. The evidence is incomplete, but it is not impossible. What the soil itself preserves is remarkable. Ancient pollen trapped in lake sediments can tell researchers which plants grew in a region and when. Phytoliths, tiny silica structures left behind by grasses and grains, survive in the earth for thousands of years. Starch grains cling to the surfaces of ancient grinding stones. Each of these is a small piece of mathematics, a count, a date, a ratio of wild to cultivated species. Researchers read these numbers the way a musician reads a score, looking for the moment when the pattern changes. And the pattern does change, clearly, decisively, right at the boundary of the Younger Dryas and the warmer world that followed. The wild grasses begin to give way to domesticated varieties. The grinding stones become more common. The settlements grow more permanent. The numbers tell a story, even if they do not yet tell us why. Whether farming arose because the climate allowed it, or because population pressure demanded it, or because something older and now lost was being rebuilt. That question stays open. The soil holds its answers quietly. Researchers are still learning how to ask the right questions of it. Beneath the waves, far below where sunlight reaches, the ocean floor holds a kind of memory. It is a slow memory, a quiet one. Layers of sediment, fine particles of shell, dust, and mineral settle down through the water over thousands of years and come to rest in the dark. Each layer is like a page, and if you know how to read those pages, they tell you something about what the climate was doing when each layer fell. Scientists have been pulling up cores of ocean sediment for decades. A core is a long cylinder of mud drawn up from the seafloor by a hollow tube lowered from a research ship. When you look at a core, you are looking at time made solid. The deepest layers are the oldest. The layers near the top are more recent, and somewhere in the middle, in cores pulled from the North Atlantic, there is a layer that marks the Younger Dryas. That layer is different. It contains different kinds of tiny shells, the remains of microscopic creatures called foraminifera, each no bigger than a grain of sand. These creatures are sensitive to temperature. Cold water species look different from warm water species. When the Younger Dryas arrived and the North Atlantic cooled sharply, the species living in that water changed. And when they died and sank, they left a record. A thin band in the sediment where the cold water shells suddenly dominate. What makes this remarkable is how abrupt that band is. The shift from warm water shells to cold water shells happens fast in geological terms, not over millions of years, not even over thousands. Some cores suggest the change happened within a few centuries. Others hint at something even faster. The exact speed of that transition is still being studied, and researchers do not all agree on how to interpret what they see. Below the ocean floor, there is something else worth sitting with. Methane hydrates, frozen pockets of gas locked inside ice-like crystals, rest in the sediment along continental shelves around the world. These hydrates are stable only within a narrow range of temperature and pressure. Too much warming, and they can break apart. When they do, methane rises through the water and into the air. Methane is a powerful greenhouse gas, meaning it traps heat in the atmosphere. Some researchers wonder whether warming at the end of the Younger Dryas could have destabilized some of these hydrate deposits, releasing methane and adding to the warming already underway. Others are more cautious. They point out that the evidence for large-scale hydrate release during this period is not yet clear. The question remains open. The ocean floor also holds clues about sea level. As the great ice sheets of the last glacial period melted, enormous amounts of water returned to the ocean. Sea levels rose, but the rise was not smooth or steady. Evidence from submerged coastlines, drowned river valleys, and ancient coral reefs suggests the rise came in pulses. One of those pulses, sometimes called meltwater pulse 1A, may have raised sea levels by several meters in a very short time. Some researchers place this pulse before the Younger Dryas. Others see signs of a second pulse near the end of it. The timing is contested. The causes are debated. What the ocean floor tells us and what we can reliably conclude from it are two different things. There is something quietly astonishing about all of this. The ocean covers more than 2/3 of the planet's surface. It holds the vast majority of Earth's liquid water. It drives weather patterns, moderates temperatures, and moves heat from the tropics toward the poles through great slow currents. And yet, so much of it remains unread. The sediment cores we have represent a small fraction of what lies down there. The ocean floor is vast, and our sampling of it is still thin. What the cores do tell us is that the system is sensitive. Small changes in one part can ripple through the whole. The balance that keeps the ocean circulating, that keeps temperatures within a range that life can tolerate, is not guaranteed. It has shifted before. The Younger Dryas is one of the clearest examples we have of how quickly things can change and how deeply that change can reach down into the sediment, into the shells of tiny creatures, into the frozen gas locked in the seafloor mud. The ocean holds its record carefully. It does not give it up easily. And much of what it knows, we are still learning to ask about. The pages are there. We are still learning to read them. There is a kind of memory that does not live in stone or ice or soil. It lives inside us, carried in the long, coiling strands of our DNA, passed down through thousands of generations, is a record of what our ancestors survived. And when researchers look closely at that record, they find something they did not expect. They find a gap, a bottleneck, a place in the human family tree where the lines grow thin and then widen again, as if something once pressed the population of the whole world down to a much smaller number. The question is whether the Younger Dryas was part of what caused that narrowing. Geneticists, scientists who study the code written inside living cells, can trace the movement of ancient human populations by looking at small variations in DNA. These variations accumulate slowly over time, like tiny marks on a long scroll. By counting them and comparing them across different groups of people alive today, researchers can estimate when those groups last shared a common ancestor. They can sketch a rough map of where people went and when, and in several of those maps, something strange appears around 12,000 years ago. Some lineages seem to thin out. Some branches of the human family tree go quiet. One theory is that the cold and chaos of the Younger Dryas killed off entire populations or reduced them so severely that only a small number of survivors carried their genes forward. The genetic signal, if it is real, would suggest that the world's human population may have been far smaller at the end of the Younger Dryas than it was just before the cold came back. But here is where the uncertainty begins to grow. Reading ancient population size from modern DNA is not a simple thing. The methods are powerful, but they carry wide margins of error. Two researchers using slightly different models can look at the same data and reach different conclusions about when a bottleneck happened or whether it happened at all. Some scientists argue that what looks like a population collapse in the DNA is actually an artifact of how the models work, a shadow cast by the math, not by a real event. The debate is ongoing and unresolved. There is also the question of ancient DNA itself. In recent decades, researchers have been able to extract and read genetic material directly from the bones of people who lived thousands of years ago. Some of those ancient samples come from the period just before, during, and after the Younger Dryas. And what they reveal is complicated. Some populations that seemed to disappear from the archaeological record do show up in the ancient DNA, just in different places. They may not have died out. They may have moved. This raises a different kind of question. If people survived the Younger Dryas by migrating, following coastlines, moving toward warmer regions, pressing into new territories, then the genetic signal we see today might not be a record of death at all. It might be a record of dispersal, of scattering, of people spreading out so widely that the connections between them grew faint. Some researchers wonder whether certain genetic lineages that appear suddenly in the record after the Younger Dryas might belong to populations that were isolated during the cold period and then rejoined the wider human world when the warming came. Hidden groups living in refugia, small pockets of survivable land, who left almost no trace in the soil, but whose descendants are still alive today. The idea is speculative. The evidence is incomplete, but it points toward something genuinely unresolved. We do not yet have a full picture of who was alive on Earth during the Younger Dryas, where they lived, or how many of them there were. What we do know is that the world that emerged after the cold ended was different from the one that came before. New cultures appeared. New technologies spread. Agriculture began almost simultaneously in several places that had no obvious contact with each other. Some researchers see this as a coincidence of climate. The warming made farming possible, so people tried it. Others wonder whether it reflects something deeper, a reorganization of the human world after a period of great loss. The DNA cannot tell us which story is true. Not yet. The ancient bones are still being found. The models are still being refined. Each new sample pulled from the frozen earth adds a small piece to a picture that is still mostly missing. Somewhere in that picture, there may be an answer to who we were before the cold came back, and who we became after it finally left. There is a question that keeps returning, no matter how many times researchers set it aside. It is not a small question. It sits at the edge of everything we think we know about early human history. And it goes something like this. What if there was a culture, a real and organized way of living that existed before the Younger Dryas, and that the cold erased it so completely that almost nothing survived? This is not a settled idea. Most archaeologists would say the evidence does not support it. The people living 12,000 years ago were hunters and gatherers, they would say. They moved with the seasons. They did not build cities. They did not leave behind the kind of record that a lost civilization would require. And that is a fair and reasonable position. It is grounded in decades of careful fieldwork. But then there is Göbekli Tepe, that site buried in the hills of what is now southern Turkey, keeps asking questions that do not have easy answers. The stone pillars there are enormous. They are carved with animals and symbols. They were arranged with clear intention, clear planning, clear effort, and they were built at least 11,000 years ago, right at the edge edge of the Younger Dryas, possibly even during its final cold centuries. The people who built them, as far as researchers can tell, had no agriculture. They had no permanent settlements, at least none we have found. And yet, they organized themselves well enough to move massive stones and carve them with skill. Some researchers look at Göbekli Tepe and see exactly what the mainstream says it is: evidence that hunter-gatherers were more capable of complex behavior than we once assumed. That is a meaningful and important conclusion on its own. Others look at the same site and wonder if it is the edge of something larger, a remnant, a memory carved in stone by people who had once known more and were trying to hold on to it. That second idea is a hypothesis, not a fact. There is no buried city beneath the hills. No roads, no writing, no clear sign of a broader civilization waiting to be found. But the absence of evidence is not always evidence of absence. The Younger Dryas coastlines are gone, drowned under 100 meters of ocean water. Whatever existed along those shores, if anything did, is now beyond easy reach. The question of a lost culture is really several questions layered on top of each other. Could a group of people have developed something resembling organized knowledge, shared practices, maybe even early symbolic systems before the cold came? Could the Younger Dryas have disrupted that so severely that the survivors scattered, carrying only fragments of what they once knew? And could those fragments have seeded the burst of activity we see in the archaeological record right after the cold ended, when farming and monument building and settled life all seemed to appear almost at once in multiple places within just a few thousand years? Some researchers find that timing suspicious. Others find it perfectly explainable. When the climate stabilized and food became more reliable, they say, humans naturally began to settle and experiment. No lost civilization required. The conditions simply became right. Both views are held by serious people. Neither has been proven. And that is where the question lives, for now, in the space between what the stones can tell us and what the water has hidden. What makes this particular question so persistent is that it refuses to close. Every few years, a new site appears, a new layer of sediment gets dated. A new genetic study suggests a population movement that does not quite fit the old maps. And each time, researchers have to ask again whether the picture they have built is complete, or whether there are still large pieces missing. The tools for finding those pieces are improving. Underwater archaeology is slowly reaching deeper sites. Ground-penetrating radar is revealing structures beneath soil that no shovel has touched. Ancient DNA is rewriting migration routes that seemed settled just a decade ago. The future of this question is not closed. It is opening. Whether that opening will reveal a lost culture or simply a more complex version of what we already know is something no one can say tonight. The honest answer is that we do not yet have enough to decide. The coastlines are still being mapped. The sediment is still being read. The stones are still being uncovered, one careful brushstroke at a time. For now, the question rests where it has always rested, just beyond the edge of what we can see, patient as the sea, waiting for the next careful hand to reach a little further in. There is a quiet way of looking at the world we live in now. You can see it in the fields outside a small town, in the slow curve of a river through flat land, in the way a city sits beside a harbor that was once dry ground. All of it, every road and farm and coastline, rests on a foundation shaped by something that happened 12,000 years ago. The Younger Dryas did not just cool the air and freeze the rivers. It pressed down on every living thing on Earth and held them there for more than 1,000 years. And when it finally let go, the world that emerged was different in almost every way that matters. Think about the land itself. The great ice sheets that covered the northern parts of the world had pushed soil and stone into shapes we still walk across today. The hills of the American Midwest, the long flat plains of northern Europe, the shallow lakes scattered across Canada. All of them carry the memory of ice. The glaciers carved and scraped and deposited. When they melted, they left behind a world with new rivers, new lakes, new coastlines. The map we know is, in a very real sense, the map the ice made. The oceans rose. They rose slowly at first, then faster as as the great meltwater pulses came. Coastlines that people had walked for thousands of years went underwater. Shallow shelves that once held forests and rivers became the seafloor. The Black Sea, which some researchers believe was once a smaller freshwater lake, may have been transformed by a massive inflow of salt water from the Mediterranean. That event, if it happened the way some geologists suggest, would have been unlike anything a human being had ever seen. Other researchers are less certain about the timing and the scale. The evidence is still being read. But here is the wider thought. The warming that ended the Younger Dryas, roughly 11,700 years ago, did not just change the physical world. It changed what was possible for human beings. The slow, cold, difficult centuries of the cold snap had kept people moving, kept them small in number, kept them focused on survival. Then the warmth returned. The rains came back to places that had been dry. Forests spread north. Animals followed the new growth. And something shifted in the human story. Within a few thousand years of the Younger Dryas ending, people in several parts of the world began to farm. They began to build permanent settlements. They began to keep records in clay and stone. The civilizations we call ancient, Mesopotamia, Egypt, the Indus Valley, all of them rose in the window of stable, warm climate that opened after the cold snap closed. Some researchers wonder whether the Younger Dryas was, in a strange way, a kind of pressure that shaped human behavior. Whether the long, cold, forced adaptations that made the agricultural revolution possible once the warmth returned. That idea is still an open question. Others argue the timing is coincidental, that farming arose from many causes across many regions. Göbekli Tepe sits in this story like a quiet puzzle. Those carved stone pillars, built before farming, before cities, before writing as we know it. They suggest that something was already organizing human effort and imagination before the warm period fully settled in. Whether that represents a lost tradition reaching back through the Younger Dryas, or simply an early flowering of a new era, remains genuinely unknown. And then there is the wider frame. The atoms in your body are old beyond imagining. The calcium in your bones, the iron in your blood. These elements were forged in the cores of ancient stars and scattered across space long before the Earth existed. They settled into rock, into ocean, into living things, into you. The Younger Dryas was one small chapter in the long story of those atoms moving through different forms. The ice came. The ice went. The world rearranged itself. Life continued as it always has, finding new shapes in new conditions. We are the children of that rearrangement. Every culture, every language, every city built beside a river or a harbor, all of it grew from the world the Younger Dryas left behind. The cold snap was not the end of anything. It was a hinge, a long, slow, difficult turning point that opened into the world we now call home. Whether a comet helped close that chapter, whether a lost culture vanished beneath the rising seas, whether the flood stories carried in human memory hold a real echo of real events, those questions are still open. They may stay open for a long time, and perhaps that is fitting. The world that shaped us still holds its secrets close. We have come a long way together tonight. We began with a world that was warming slowly, a world where ice was pulling back and rivers were finding new paths through soft, thawing ground. We watched the cold return without warning. We sat with the silence that followed the quiet left behind by vanished forests, by animals that walked into that long frost and never came back out. We wondered about the people who lived through it, who carved stone and planted seeds, and told stories about water rising over everything they had ever known. And now, at the end of all of it, the question is still open. That is the honest truth. After all the ice cores and the sediment layers, after the platinum spikes and the burned soil and the drowned coastlines, we still cannot say with certainty what began the Younger Dryas or what ended it. We cannot say whether a comet touched the sky above a frozen continent. We cannot say whether a civilization, small, scattered, or perhaps more organized than we expect, was swallowed by rising water and time. The evidence points in several directions at once, and the researchers who study it do not all agree. Some of them believe the meltwater pulse from Lake Agassiz, that vast, cold inland sea sitting on top of North America, poured into the North Atlantic and broke the ocean's great circulation, that the pump stopped, that the warmth stopped moving north, that the cold came back because of water, not fire from the sky. Others look at the black layer in the soil, the nanodiamonds, the glass beads that only form in extreme heat, and they say something fell, something burned. Both ideas carry weight. Neither one is settled. What we do know is that the world changed quickly, in ways that left marks we are still reading 12,000 years later. Göbekli Tepe stands in the dry hills of what is now southern Turkey. Its carved stone pillars, older than any city we have a name for. The people who built it were not supposed to be capable of building it. Not by the old story we told ourselves about how civilization grew. And yet there it is, waiting, asking a question we have not yet answered. One theory says it was a ritual place, built by hunters who gathered in seasons. Another says it hints at something more organized, more connected, more lost to us than we realize. The stones do not say. They simply stand. The flood stories persist too, across cultures that never met, across languages that share no common root. The memory of water rising lives on. Whether that memory traces back to the Younger Dryas, to the Black Sea flood, to the drowning of coastal shelves that once held human settlements, we cannot say for certain. It may be that the human mind simply reaches for water when it imagines catastrophe. It may be that something real was remembered and passed down through 10,000 years of telling. Both possibilities are worth holding gently. Tonight, the planet is still here. It has carried all of this, the cold, the fire, the flood, the silence, and it kept turning. The oceans that swallowed those ancient coastlines are calm now under the moon. The ice that remains in Greenland still holds its record of everything that happened, layer by layer, year by year, waiting for someone to read it more clearly. The soil beneath old forests still holds its black layer, its quiet evidence of something that passed through. And somewhere, under shallow coastal water, under sand and silt and centuries of tide, there may be a floor of an old valley, an old hearth, an old path between two hills that people once walked. We have not found it yet. We may find it, we may not. The ocean keeps its own time. What is certain is that the earth has always changed. It has always moved between one state and another, sometimes slowly, sometimes in what feels, by geological measure, like a single breath. Life has always found a way through the cold and the dark and the sudden heat. Humans, in particular, have always found a way through. You are part of that long line. You carry, somewhere in your cells, the memory of people who survived the Younger Dryas, who looked at a changed world and kept going. That is not a small thing to carry into sleep. The question remains open. The door is still ajar. And that is exactly where it belongs, open, quiet, full of possibility. Subscribe for a brand new Earth topic every night. One tap, and something wonderful is waiting for you tomorrow. Sweet dreams.